Hey guys, this is Professor Janacek, and I want to go over the vector operation of dot product. So suppose we have two vectors, u and v, and they're non-zero vectors, and the angle between them we'll call theta, where theta is anything between 0 and pi, inclusive of those two. The dot product, u dot v, has two definitions. We could think of it as the magnitude of u times the magnitude of v times the cosine of the angle between them. We could also look at the dot product as taking the components. You're going to take the product of the first components plus the product of the second components plus the product of the third components, if there are third components. I want to point out that this is a scalar value. It is not a vector value. Also, it turns out that if u is the zero vector or v is the zero vector, then of course the dot product between u and v in either case is the scalar zero. Notice this is a scalar. And in this case, the angle between them is undefined. We also know that two vectors are parallel if their dot product is equal to either a positive or a negative times the magnitude of the products of the two vectors, meaning the cosine of theta is equal to 1. Cosine being 1 is whenever that angle is 0 or pi. And that would make the two angles parallel. The angle between them is either 0 or pi. Notice if the angle between them is 0, then they're going in the same direction. If the angle between the two vectors is pi, then they're actually going in opposite directions. Two vectors are considered to be orthogonal, which is another way of saying vectors are perpendicular, if their dot product, u dot v, is equal to 0. And this only happens when the angle between them is pi over 2, because in this case, the cosine of the angle is 0. That's how we get the 0 for the dot product. Again, this happens when the angle between them is pi over 2. And again, that's what it means for two angles to be orthogonal, that the angle between them is pi over 2. We do have a few properties. The dot product is commutative. We could also look at scalar multiplication. Notice I've got a scalar c times a dot product. And we can multiply this in a couple of different orders. Either way, we would call that an associative property. We can associate the scalar with u or associate the scalar with v and then take the dot product. And we also have a distributive property for dot products. If I have u dotted with the sum of v and w, I can rewrite that as u dotted with v plus u dotted with w. So again, a distributive property. Projections of u onto v, we also refer to these as orthogonal projections. And a nice way of thinking of it is thinking of them as shadows. You often hear that word, orthogonal projections or shadows. Let's see, if our angle is between 0 and pi over 2, then our projection, just so you see what that looks like, I have u and v, and the projection of u onto v is sort of like its shadow down here. So I could just think of dropping that u vector down onto v, and that is the projection. The projection is the magnitude of u times the cosine of the angle between them times vector v over the magnitude of v. Notice this does end up being a vector value. Also notice the notation. I've got the projection onto v of u. So notice I subscript the vector onto which we are projecting. If we're looking at the angle being between pi over 2 and pi, then the way we would do this, the way we would consider this shadow is I would actually think of v going in the opposite direction. So I've got this opposite value here, and then take its shadow. And so this would be our projection here. So in this case, the projection onto v of u, that's how we're going to say that, is the opposite of the magnitude of u times the cosine of the angle between them times the opposite of vector v divided by the magnitude of vector v. Very, very similar. You just end up with some negatives in there, so be careful with all of that. There is an application if F is a constant force applied to an object producing a displacement of d, and we have this angle theta that is between those two. Turns out work, maybe I should put that in here, work is what we're looking at. That is defined to be the dot product between F and D, the force and the displacement vectors. Of course, that is the magnitude of F times the magnitude of D times the cosine of the angle between the two. And there you go. Enjoy!